where we are in the course. So have a listen. We're going to do our notes and homework on here. Brand new stuff, which I'll explain in a second. This is our last new lesson of Unit 2. Tomorrow will be a quiz review. The review is going to be just like the quiz on Friday. So quiz tomorrow, quiz on Friday. Quiz review tomorrow, quiz on Friday, sorry. Not going to have a test over these 3 sections, okay? It's just going to be the quiz, which means it's like a 30-point quiz. All my quizzes are 30 points. And so it'll just get in there with all your quizzes, and it could be a dropped one, but I don't think it will need to be, okay? I made the review just like the quiz, and then we're done with Unit 2 on Friday. Except for Monday, bring your laptops because we're going to do the progress monitoring thing on College Board, which is a completion grade. You might have a sub that day. So Monday we'll be just doing the progress check for points. Tuesday, you get your new packets of last unit, Unit 3, and we start Trig. Okay, so that's where we are. Trig will probably take us a little bit into quarter 4, and then it's all review until May 13th, which is our test day. Okay, so let me tell you about section 2.15. It has given me the most stress of all the sections so far this year, and there's been a lot that we've done in here. Because when I first started looking at it weeks ago, I was like, what the heck are semi-log plots? Being completely honest, I never heard of them. And I went through all of the other notes and examples, and I was like, this is like going to take me a week and a half to teach. Honestly, it was so in-depth. So then I looked at this guy's stuff, and I was like, okay, totally understand it. What really is this, though? Why are we using it? So, and I'm just being honest with you, reaching into this section, I was like, okay, I need a little help. So anytime I need a little help, I go to see Mrs. Springer, who's our AP Calculus teacher. And so she looked at this, and she goes, I've never even heard of them. Okay, this is not a good sign. Dig deeper. I spent a lot of time on this. And I realized this is super cool. This is such a cool concept, and you're going to think it's pretty easy and everything because of all the work I've done. Let me give myself a pat on the back. But really, it's all we're doing with semi-log plots is changing the y-axis to make. Thank you so much. There's notes on your desk that we're going to be working on. All this is changing a y-axis a certain way to make data easier to look at. That's really it. And it's very science-based, and if you have bio tech, I don't know if you've done it yet or if he does do it, but when it has a lot to do in science with like taking huge amounts of data, and it condenses them all into quadrant 1. And when it's used as like with splicing DNA or some such thing, here's a great, is that the door? I wish I weren't recording, so I was going to say something that has nothing to do with that. Hi. Do you have Miss Blaylock this period? Who's giving you these? Okay. Because I was interrupted, like, it's not your fault, 20 times last period, and okay. I just want to know who the email. Thank you. I'll wait till and then I'll talk about people. Okay. What was I saying? Oh, so here's a good visual, just an example of what just before I even get started, sum it up. Here's a very small amount of data, right? These are just regular old points on a linear graph plotted. But when we change the y-axis, the way I'm going to show you, what happens is your data is still the same on here. It's the same ordered pairs. But by changing the y-axis a specific way, it puts everything in quadrant 1, kind of condenses it, makes it easier to look at, and it changes the shape. Look how a line, when we graphed it, this is actually what a log graph would look like, okay? So it looks different, but it makes for easier evaluation of it. We're not really going to be dissecting what the points represent. We're just kind of hitting it on the math end of it. And so that's what this is about. So this is not a great example, but just real quick. One thing we want to know, remember I said it condenses data into like one quadrant. It also changes the shape. And what we're going to focus on is this right here. This is the key to everything. With a semi-log plot, which I haven't explained well yet, where the y-axis is logarithmically scaled. That's what they say, logarithmically scaled. Exponential data, exponential functions will look linear, okay? So that's really, 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 really important, okay? So what I have here is, I'm going to just kind of sum up. It's the blah, blah, blah data that has to do with exponential growth, okay? We have an x-axis of years, and over the years, the population, which is the y-axis, is growing exponentially, right? This is an exponential function. And what this is all about is the y-axis. This is scaled linearly. This is scaled, look up here, linearly. X and y-axis are both linear. What does that mean? It means the change is constant, right? You're counting by fives, you're counting by ones, you're counting by hundreds, you're counting by thousands, okay? The scale can be different, or intervals, but that's linear. Look over here. We're counting by, this is 10 to the first, this is 10 to the second, and this is a really kind of a bad example, but just trust me, this is logarithmically scaled. You'll see it more in a second. But it starts to look linear over time. Same data, but the picture is different, okay? So just keep that in mind. Now let me show you a good example, a better example. Look down at example 2. And by the way, I know that the notes I gave you today are really small, and especially looking at these graphs, I apologize. Don't stress too much about that. If you're understanding, especially looking up here, that's what's more important, okay? So just know 120-something students, 8 pieces of paper to copy and hole punch and get to you. I had to do, so you'll be doing some flipping and stuff. I apologize. Okay, so yours says Mrs. Morse. But after Mrs. Morse tells another one of her hilarious math jokes, it begins to spread around the school. The number of people, P, that have heard the joke after T minutes is graphed on the semi-log plot above, where the vertical axis has been logarithmically scaled. Okay, so which of the following functions could represent this data? So let's look at how it's scaled. The x-axis we're not messing with. These are always going to be linear, exactly spaced. And you can see the spacing. It's exactly the same. We're counting by ones in this case. The y-axis, though, look closely at the y-axis. It is scaled logarithmically. And what that means is they're all base 10s. Like this is 10 to the 0 power, which is 1. So everything between 1 and 10, we're just counting by ones. It's, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, normal. But then look what happens. This is 10 to the first. Let me use a different color, right? 10 to the first is 10. And all the way up to 100, what are we counting by in here? Tens, right? So this is 10, 20, 30, and so on, okay? And then we get to 100, which is 10 squared. And we go all the way up to 1,000. Now we're counting by hundreds. Do you see how between each equally spaced interval, we are spaced differently? We're counting by ones, we're counting by tens, we're counting by hundreds. And it keeps going. And of course, this is 10 to the third, and it keeps going. That's what the y-axis will look like in these types of problems. This is a semi-log plot or semi-log graph. That's what it means. Semi is half of it is log. The other half is not. Okay? So what we just learned, we circled at the top, is that a linear graph, this is clearly a line, right? A linear graph on a semi-log plot means the original data, or on a regular graph, what would it look like? What would it have looked like if this is for you, Sadie. One for Sadie. Okay, all this is, let me tell you what it is so you know you're not like rushing to get it. There's a flyer that you guys were emailed apparently, or on Canvas, or blah, blah, blah. That's about an SAT prep course if you want to take it on the weekends. I'm not sure. But all last period, I sent kids up on these passes. I'm not kidding, like 10 kids. And there was like 10 different runners. Like it was just the door kept. And I was like, okay, go, because it says ASAP on it. And they went and they just got a flyer about this SAT review. So, of course, you want to get it, maybe because you don't open Canvas, but you don't need to go right away. So, people that I'm saying, this is not, oh, and Michael and Sadie have gotten one. So, guys, go in a little bit, okay? All right, back to this. Let me get back to this. What would it have looked like? If it's linear now, what would it have looked like on a regular old-fashioned graph? Yes, Sadie, that was perfect hand motions. It would have looked like an exponential function, where this was like 0 to 5, and this would have been 0 to 1,000, but counting by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 1,000, counting by whatever, okay? So which one of these could be this information backwards? Which one of those? A, B, C, or D? Why D? Hi. Thanks so much. Appreciate it. And Amanda and Brandon. Why would it be D, my loves? Somebody said it, and they were right. Why is D? Because it's what? What is this? Exponential. Exponential data, exponential functions look like that. That's the only one that's got that. Okay? Linear is y equals mx plus b. Okay? So, for the first reason, this is the only one that has that information. Okay? And we're going to go deeper into that in another problem. Okay? So, being able to pick an equation that matches this. Okay? Because if it's linear, understand this connection. If it's linear on a semi-log plot, on a regular old XY chart that we've been using our whole lives, it would look exponential. So the data actually would come from an equation like this. Okay? That's the huge takeaway of today. All right, look at the next one. Example 3 takes up the whole paper. This is another type of problem you're going to see. The table above gives selected values for the function f. Which of the following graphs could represent this data in a semi-log plot where the vertical axis is logarithmically scaled, right? If these are regular old-fashioned boring graphs, we would say pretty much they all look like lines. Maybe this one's got a curve to it. We'd say, oh, they're linear, but because they're on this special type of graph, they're not actually that. Let's look at the table of values they gave us. We've had to take a table of values in the past and evaluate what type of information, what type of function does it represent. Are we adding the same thing as we go left to right? That would be linear. Are we multiplying by the same thing as we go left to right on the y values? That would be exponential. That's what's happening here. So I'm not adding the same number, right? There's adding 20, adding 30, adding whatever. So that's not linear. Doesn't seem to make sense, except for what we just learned. But what it is actually exponential. We are multiplying by the same number. Now, most of us, including me, I'm not going to lie, can't just look at that and tell you what we're multiplying by. But to find it, remember it's finding B or R, we called it sometimes, you're just dividing in reverse, right? If I divide in reverse any two consecutive numbers, what I get is what I'm multiplying by as I go left to right. So I'm multiplying by 1.5, 1.5. That makes this exponential. That makes it this form if we were going to go that deep. Okay, so just make that connection. So which one of these graphs matches that? Well, we know an exponential graph now, we just learned it, on semi-log plot paper will look linear. So we know one of them has to be a line, okay? And sometimes they may not be perfect lines, so I'm not going to get too judgy on that part because I could almost make a case that this is linear starting at a certain point, whatever. Okay, but let's look at what the graphs look like. That's more important. One thing we do know is that the first point is 140. So that should be a point on these graphs, okay? Because the points don't change. The points are the same. It's the graph that changed. So 140, on this graph, it's 1 point whatever. It can't be that. Plus the y-axis is not scaled logarithmically. It's counting by the same exact thing the whole way through, okay? Same with this one. This could be logarithmically scaled. and just really zoomed in to like the first quadrant, like the first right here, because it kind of looks like it. But again, 140, this is not 40. If this is 10, this can't be 40, okay? So it can't be that one. These both, without spending a lot of time looking at it, because we're going to talk about it on the last page, both of these have 140 graphed on it. But which one of these has the y-axis the way we want it for semi-log paper, semi-log plot? D, right, William? So again, this is counting by tens, but it's counting by tens the whole y-axis. That's linear. It's constant the whole way. But this is counting by ones, counting by tens, counting by 100. That is what we're looking for. And this is linear. You could match all the points up with that. So no work to show or anything, just D. That's the answer. Okay? On the next example, it's going to be hard for you guys to do on that little paper, but it's really simple concept. Don't worry about it too much. This is number 1 and 2 on your homework, and you don't need to do both of them. You'll see when we get to the homework, and I'll tell you again. If you just pick one of them to do, because it's kind of busy work after you understand it. But I do have the answer key for both, so if you wanted more practice, I'll tell you later. So we're just going to plot these points, A, B, C, D, E. We're going to plot these points. So semi-log, right, 1, 10, 100, 1,000. So 0, 200, that's going to be on 0 is X. And then 200 is between 100 and 1,000. So if this is 100, this would be 200. And I know it's hard on your graphs, just do the best you can. 125. So X is 1. 25 would be between 10 and 100. We're counting by tens in here. That's 10, 20, and then somewhere in between those two lines. Right? Stop me if I'm going too fast. 2, 7. So to the right, 2, up 7. 7 is between 1 and 10. So I'm going to go up 7 or backwards 3. And I can't really see, so just assume that I'm on the 7. Okay. And then 3.2, 800. So here's a chance to look at how the x-axis is counted in between each of the single digits here. We're counting by 0.2. So 3.2, 0.4, 0.6, 0.8, and then 10, which would get us to 4. So 3.2 would be that first tick mark. And then 800 is between 100 and 1,000, so two shy of 1,000. Right? So just 2 below 1,000. And then lastly, 4.6, so 2, 4, 6, so I'm going to be right here. Up 1.5, so that's between 1 and 10, 1 and a little bit more. Okay, so being able to plot the points or pull points off a graph is just testing your knowledge of how this is scaled. Okay, we good with that? Okay, last example. This is the only one that you could have problems with. So if you're kind of like dozing off in your brain or literally, try and pay attention to this. Not hard, but you definitely need my explanation on it. So those of you watching the video, this is where you definitely want to tune in. What we're going to do here is, see, we have a log, semi-log graph. It's already graphed for us. Let me read. The semi-log plot above corresponds to the data table for example 3. So the problem we just did in example 3, we already did some work on it, so I'm going to grab it for us and put it here. It's this. Okay, that's example 3's data. And what we're going to do is just part A of this, and same in the homework, that you won't do part B. Part A asks us to write an equation for the linear model. Okay, so let's review. This is a semi-log plot with a linear looking graph on it, right? This is a line, but we know before it was this, it was this, right? It's just when you put it on this paper and change the y-axis, it comes out looking linear, okay? So what we're going to do is write the equation of this line. But some things have changed a tiny little bit. Our y values have to be in log form. It can't just keep it as your normal y's, and I will explain this. Understand this fancy looking craziness is very, very simple. This is your slope, and that's your y-intercept. It's still slope-intercept form. It's just your m and your b, we take the log of it. Okay, so what am I talking about? Well, I know to write an equation in slope-intercept form, I need two things. I need the slope, and I need the y-intercept, right? So we're going to find those two things, and we're going to let the table help us, okay? So with me, do me a favor, and we're going to recreate, do it with me though so you don't do it wrong, this XY chart on this paper. I'm just going to grab a few points. You really don't need that many. And I'm going to add something. I'm going to add x is 0. They didn't give us 0, if you look. They started at 1, and they went from there. So I'm just going to grab the numbers I know, which are 4 and 6. So I just, by the way, again, just took them right off this. And I'll come back to why I put 0 there in a second. I'm going to add a third row. I did mean to go down that far. Because if you remember, I said we're going to need log of just our y values. Why just the y values? Well, our x-axis is regular old linear numbers. We don't change x. So in a minute, we're going to need log of 40 and log of 60. And it could keep going, but we only need this many points. This is plenty of points for us. So let's go back to what we're trying to find, slope. Let's start with that. We want the slope. If we take 2 points off this graph and plug them into, if you need me to write it, I don't know, slope formula, hello. Okay, thanks so much. Have a great day. The student's fault. It's not the student's fault. It's like, seriously, guys, you're witnessing it. Witness, witness, witness. I'm going to put my boxing gloves on. I'm not kidding. Okay, let's keep going. To find slope, and guys, we've been calling it this, and you're going to see that more than you're going to see slope. What does AROC mean? Average rate of change. Why are we saying AROC instead of slope? They're really interchangeable for this. Slope is for a line. That's it. It's constant the whole way. It's going to be the same. AROC is average rate of change, slope, between any 2 points on a curve, too. So AROC is like an umbrella term, and slope is specific for lines. So you might see both. So I'm just going to go ahead and plug in. I want to subtract all you need is 2 points. Any 2 points on a line. Don't forget what you already know. I'm going to do log 60 minus log 40. Those are my two logs. We're in log land right here. Log 40 over 2 minus 1. Right? We don't change the x's. And we just put that in our calculator. And you're going to get weird decimals, crazy decimals, okay? Be comfortable with that. But I want to ask you, guys, why this is wrong. Why is that wrong? Because it's wrong. So important, guys. If your calculator opens parentheses, if you keep typing in there, it's doing log of all of that versus log of 60, that minus log of 40. And it's so easy to forget those parentheses. So easy. Because you're going to see, and notice you don't have to close your parentheses at the end. If you're hitting enter, you don't have to. You get crazy decimals either way. They're both positive. It's a line with a positive slope. So you might not catch that is the actual answer. Let's go out 3 places. Half of our answer done. Got our slope. Now we need the y-intercept. That's what B means, right? B is where this line crosses the y-axis. In your homework, there's 2 of these. One of them, they gave you 0. They gave you the chart. You can just grab it. But if you don't have it, we have to find it. So that's why I put the 0 there, because if a line crosses the y-axis, x is going to be 0. So we need x is 0. Okay, let me go back to our data that we just talked about. I'm almost done too, guys. What we already know is this is exponential, but we need this number, and that's what I added there. How can I find this number on this XY chart? How can I find it? Divide 40 by 1.5. That's right. If you're multiplying by 1.5 to the right, we would divide going to the left. So, don't forget though, oh no, not yet. 40, divided by 1.5, right, going backwards, gives me this weird number. And sometimes you get this decimals, but let's just see. And this one happens to be able to change to a fraction, so it's just a little bit cleaner to put the fraction in there, but it's 26.6 repeating. But don't forget you're going to do log of that. Log of 80, 30, 80 over 3, I keep saying 30, is that the right answer? Did I do that right? Doesn't look familiar to me. Let's make sure. Yeah, that's right. 1.426. So B is 1.426. You're going to get weird decimals, and that's your final answer. So really, you're doing the same steps you've always done to find slope-intercept form. Take 2 points, find the slope, and then wherever x is 0, y is your b. But in this case, anything that has to do with y, you have to use this column, okay, for this graph. Okay? It's a little confusing. It's nice when they give you the 0, but just know the XY chart is going to be exponential on the graph that looks linear. That's the key to life today. Okay? Let me show you what your homework is. It's on there somewhere, C7. 3 through 7 and 10 are multiple choice.